This is Paul Gregg, and I'm going to make another video. This one's about Alka Seltzer rockets. We did this at the high school, and then I repeated it with my grandkids. And it's a bit of an odd thing for me to do because I don't have great conclusions here. But I will tell you what happened to me and maybe provide some insight if you're thinking about doing Alka Seltzer rockets. So Alka Seltzer is a medicine that it's a combination of sodium bicarbonate, aspirin, and anhydrous citric acid. Now, the sodium bicarbonate and the anhydrous citric acid, when you mix that with water, it produces carbon dioxide gas. The aspirin's just there for pain relief, I guess. But um, so when you combine that, it produces carbon dioxide gas that in a closed volume that results in an increase in pressure. So there's a lot of things you can learn from this Alka-Seltzer rocket experiment. You can know something about materials and energy and flight and propulsion and flight stability and chemistry. So there's quite a bit you can learn from here, but it's quite broad. And I will concentrate on things I know about and mention some things I'm not that good at, and then just take it for what it's worth, I guess. So the basic idea is you have a film canister. This used to be what we held film in before the digital age, and they were fairly water airtight containers that a roll of film would fit in. And you can get these online, and probably most of them now are used for this Alka-Seltzer rocket experiment. So this is what it looks like. I did download a model into my CAD program, Fusion 360, which I can use for free. And this is a model of it. And then I cross-sectioned it and looked close at it. So here's what's going on. So the pressure is on the inside. One end is sealed, the other end has the cap on it, and there's this little lip on the cap and a lip on the canister that interlock, and it interlocks fairly well. But as I found out, it's not super airtight, and you can tell these red lines as the pressure increases. So as you put water, some amount of water in the canister, sitting upright, and then you throw in some portion or all of a Alka-Seltzer tablet and you just pop the cap on. And that's a very important thing you have to do pretty quick. Um, and then you turn it upside down and you let it sit there for some number of tens of seconds, and then it'll just all of a sudden pop off and the canister will go flying up in the air. And and I guess the objective is to ask ourselves, how do we make that happen? How do we make the best rocket that flies the furthest or something like that? So there's a lot to cover here. Looking at this cap, and I concentrate on this cap because I think this is where a deficiency is, at least in the film canisters that I ordered online. Um, they all leaked. And I don't know if they leaked consistently. Leaking consistently is something I can deal with. Leaking inconsistently is, as the cap gets used, as it gets popped off and on a couple of times, does it change? And that's really what makes this experiment difficult. I did this at the high school, then I did it with my grandkids, and we did better at home than at the high school as far as consistency, but it still didn't launch every time, which means there's a leak and it's not, maybe it's not consistent. So, but if you experiment, you do an experiment and it turns out that what you wanted to happen didn't happen, that's that's just as valuable because you can draw a conclusion and you can see how to do it better the next time. And so you start your experiment with kind of a thing in mind of how that's going to turn out. Or somebody on YouTube, it turned out this way for them. And if it doesn't turn out that way for you, you have to just document that and say, this is what happened. And a good scientist doesn't have those preconceived notions. You can have theories about what's going to happen, and you can think about it, but you really have to document what really happened and why it happened, and then maybe repeat it. So the pressure builds up inside the canister and on the lid, And then it gets to a certain point. Now, these red lines I'm putting in as an exaggerated deflection of the cap and exaggerating deflection of the cylinder, okay? The canister. And you can think about these motions and which ones are going to make it come off sooner or make it come off later. But what happens is finally the force on the cap gets big enough to overcome this lip, and it pops off. And this is upside down, but the canister goes up and the cap stays on the ground. One thing I thought is I believe I didn't find any, but I believe there's a cap with a reverse lip. In other words, this shows the lip on the cap on the inside of the cylinder. Now, if you could make the cap on the outside of the cylinder, so the cap came over the outside here, the lip was here, and then a lip on the outside of the canister. That might be better because then the pressure is tending to seal the cap. Okay, and this is when we make airplanes, the doors on an airplane seal on the fuselage, the hole in the fuselage. They seal on the inside of the fuselage. And that's because the pressure inside the airplane, when you go up to altitude, the pressure is helping to hold the door in place. And there are some mechanisms and bolts and things, but they're really, they're there to hold the door, but to hold the door in a place where the pressure seals the door against the cylinder from the inside. So that's why doors seal from the inside on an airplane. Okay, there's a bunch of word charts here, and I'll go through it really quickly and get to the more interesting stuff. So here's the hypotheses. You say, let's see, I'm thinking about a lot of variables we could do with this. Is more water or less water better? Um, you can experiment with that using less water, more water. You can have full tablets or partial tablets. That increases the surface area of the tablet, which makes a little difference. Uh, um, will warm water cause the rocket to launch quicker? Probably does, but it's it's difficult enough to sometimes to get these caps on and get the thing situated so it's going to launch. And it may not increase the performance. It just may launch quicker. Uh, it's going to launch when the pressure is a certain value. And and so I don't know if hot water, cold water, you can certainly do experiments with hot and cold water and room temperature water and see what the difference is in performance. Um, I thought because of this situation here, if I put a piece of tape on the outside of the film canister, that might help build up higher pressure. And so I thought maybe if we had some tape, we could put one or two layers on the outside of this. You do have a little bit of weight going with the rocket because it's got tape on it, but if the pressure is significantly higher, then maybe that's a good thing. What's the optimum launch angle? Okay, so at the high school and with my grandkids, we launched them. We started out launching them straight up. The trouble with that is it's really difficult to quantify how high it went. You can have essentially a large ruler against a wall and have people looking at it, and you can even take slow motion video and get pretty close to that. But an easier thing is to launch it at an angle and then see how far it goes. Um, so optimum launch angle. And as long as all the rockets are launched at the same angle, it should be fair. But it's an interesting side question. What angle do you launch any projectile at to where it will go the furthest? And we can cover that in a little bit. Mathematically, you can figure out what that is. If you have fins on the back of a rocket, uh, does that stop the tumbling? If it's going to tumble, and we'll talk about that in depth. Will a weight on the front of the rocket stabilize the rocket? But it increases the weight, so maybe it decreases the performance, but I'll show you why the weight on the front of a nose of a rocket can stabilize it and keep it from tumbling, and maybe that makes it go further. A nose cone, and we'll talk about aerodynamic drag. I have a good chart from NASA on that, and we'll see how that works out. And then breaking the tablet into pieces, will that make it? We could even crumble it into little pieces and the surface area gets really big. And it's really the water and the surface area of the tablet that are making this gas. So if we increase the surface area of the tablet by breaking it into pieces, does that mean it's going to, well, for one thing, will the pressure, will you achieve a maximum pressure quicker? And then, like I said, with the hot water, does that mean an increase in performance? Performance would be how far it goes or how high it goes. And even if we do break up the tablet into pieces, did it increase the performance of the rocket, or just did it go off quicker? So this is what you need to have: Alka Seltzer tablets, film canisters available on Amazon or anywhere, water, different temperatures, a scale to weigh the water and the tablets, tape, because I'm going to try that, and a long, like 100-foot tape measure or 100-meter, well, 50-meter tape measure. Generally, I haven't seen these rockets go much further than 60 or 70 feet launched at an angle, but we'll talk about that. Um, oh, nice fins are these really thin plastic foam sheets and hot glue guns. You can make fins out of that, and then a stopwatch. Just you can see, you could just measure how long each flight is and shoot them up in the air, and maybe that's a way of us. The one that is in the air the longest is the one who launched the best. So initially, with my grandkids, we found that every one of our canisters leaked at some level, and so you had to have quite a bit of water in it, or else, because once the water leaks out of the cap, then air is leaking out of the cap, and it leaks a lot faster than water because water's a lot denser. But still, most of them went pretty far, and some of them didn't launch at all. Um, so we did switch to a 45-degree launch and then measured the distance. And as long as they're all at 45 degrees, that's fair. We tried the partial tablets, but a lot of those, they didn't launch at all. And so we just went to full tablets. Because every rocket leaked, it's impossible to determine how much air was in the canister when it launched. And so it makes all of that kind of thing suspect as long as you don't have as long as it leaks. So I really should try to get a canister that seals on the outside, or a better made canister. Um, and you know, before you get a repeatable seal on the film canister, um, I don't know if you can put too much credence in the results. So here's the deal. There's a question like, okay, if I fill this totally full of water and turn it over, put the tablet in and turn it over, it's sitting there building up pressure. And as the cap leaks, the water level goes down as the carbon dioxide gas. If I don't have any air in there in the first place, then it's all carbon dioxide. And the question in my mind was, is it better to have all carbon dioxide in there, or an air? Is it better to have mostly air in there? And so I determined that carbon dioxide actually is denser than air, and that leads me to. And there's some links here, and I thought maybe that would be a good thing. Of course, this is based on the fact that all of our canisters leaked, and it's kind of like you put it in, it starts building up, you can see the water leaking out, and then it goes off at some level that I don't know what it was. But if it takes long enough that all the water goes out of the canister, then the air leaks and you're done because it's not going to launch. So here's kind of we're following the energy here, okay? When the cap separates, the pressure on the cap is released. So basically, for a split second, the pressure is pushing on all the sides of the cylinder, and it's pushing on the the cap of the end of the canister, and it's also pushing on the cap. And so there's these pressures. And for a split second, when it releases, that pressure is still on the front. If this is the cap on this end, this pressure here is still on the front until the water gets out of there. And so for a split second, there's this pretty good force that's chucking the the canister in one direction. And there is an energy thing where the mass of the water is going one way, so the mass of the canister is going the other way. It's one of Newton's laws that for every action, there's an equal and opposite reaction, and that's part of it too. But the mechanism for doing that is the pressure on the front, and it just lasts a very short amount of time, some fraction of a second. And but that force is enough to accelerate the mass of the um, canister to pretty good height. So one thing you want to do from an engineering standpoint is follow the energy. Where's the energy going? This energy is caused by CO2 being formed. This gas is forming. It's in a most pretty much contained volume. The volume does change a bit. And so the mass, the energy is stored in the compressed gas. It's also stored in the stretched sides and ends of the canister and end caps. And so we can talk about that. It's I don't spend too much time on this, but basically, material is. I won't talk too much about this. This is a stress strain curve for the plastic material, or for any material, and we want to, if you get to this point where you've gone past the yield stress, then there's permanent deflection in the plastic, and you don't want to do that because, well, you can do that, but the container would be a different shape when you were done with it, and so. Um, we won't cover that too much. Now, during flight, how do we first off, you got to observe whether your canisters just by themselves are flying straight or not. Okay. But in all rocketry and airplane dynamics, you have a center of mass, which is the geometric center of where the mass is, and you have a center of pressure. And that is defined as well. There's other videos by competent people who can tell you what the center of mass and the center of pressure is. Center of pressure is if I was if I had if from the side, if I was blowing into the screen on this thing, would it tilt up or down? Would the nose tilt up or down? And if this red dot with the white dot in it, if that's in the center of pressure, then it wouldn't tilt either way. Whereas if I was holding the rocket on a fulcrum, on a point, whether it would tilt forward or backward, that's the center of mass. And it's generally it's kind of a rule if you want this to fly well for the center of mass to be in front of the center of pressure. Okay. For it to be stable. Now, there are times when you want to not to be too, if you want a rocket to turn really fast, you want the center of pressure to be just barely behind the center of mass, because then it's really easy to turn. So, and you can, if you have a model rocket, you can tie it to a string at its center of pressure and fling it around your head and fly around. And if it flies in a straight line, then you're good. Well, it's an indication that you're good. So here's for this canister, I put it in my CAD program, and one end is open, the other end has a solid cap on it, and so the center of mass is slightly ahead. The center of mass is slightly forward of the middle of the cylinder. Okay, and I in Fusion 360 I could determine where their center of mass is for this canister. The center of pressure obviously is right at the center point, okay, halfway. And so we do have a case where the center of mass is a little bit in front of the center of pressure. This is like if you had a fulcrum here and you were um, holding this, it would be a little bit forward. So by theory, the cylinder shouldn't tumble too much. If it does, you can either add fins or add a bit of weight to the nose. And you might want to do that with a nose cone. Now here we're covering drag. So we've got this velocity of our rocket going through the air, and the force that started it is from the explosion, if you will, of the Alka Seltzer gas, the CO2 gas, and the cap coming off. And so that force, but it's slowing down the whole time because it has drag. So it has a velocity vector going one way and there's drag going the other way. And if you wait long enough, it'll stop because everything has drag, air drag. If you're launching it in space, you wouldn't have air drag, but if you're launching it on the Earth, you're going to have air unless you put it in a vacuum. So the drag, that's a force equal to this coefficient, drag coefficient, times the density of air times the velocity squared times the area, the frontal area of your shape divided by 2. Okay, now velocity is very important. So we're not going very fast. And so this drag won't be a very big component no matter what you do. Once you start to go really fast, and you can feel this in your car if you stick your hand out the window. The Going from 0 to 40 miles an hour, there's a certain amount of force. But if you go up to 50 miles an hour or 60 miles an hour, there's a lot more force than there change in force than there was from 0 to 40 miles an hour. And that's because the velocity is squared here. Okay, it gets a bigger impact. And the other important thing here to look at is look at these. This is from NASA and their drag coefficients that are determined experimentally. You could nowadays determine these with analysis in a computational fluid dynamics, and they probably have done that. But this is standard over the years. A sphere, the drag coefficient is 0.47. Now these are kind of for reference to each other. Okay, so if you had a cube flying through the air, um, it would have a drag coefficient of 1.05. And that's twice as much as a sphere. That you'd expect that. More streamlined things have less drag. A cone is 0.5. It's pretty good, half sphere. But then you get down here a long cylinder and then a short cylinder, which is kind of what we have, a short cylinder. The drag's pretty high, 1.15. And if you can streamline that with a nose cone or something, the drag goes way down when you get really good at streamlining something. So this is why, this is just basic aerodynamic drag. And we can put a nose cone, if you put a fairly light nose cone on this canister, that'll put a little bit of weight in the nose too, and it may help it to fly straight and fly further. So here's what I designed a launch pad. Instead of just putting it on the ground, in order to measure the distance it flies, I made a launch pad that has 3 positions, 30 degrees, 45 degrees, and 60 degrees. Okay, and that just makes it easier to measure the distance it flew. So you select the position here, place the cap in the hole. There's kind of a hole that holds it in the board. Insert the tablet, snap the board onto the top of the cap, and flip it over and wait. And that's kind of the procedure. Understanding the laws of motion. And this is I'll go through this. I'll go through it fairly quickly, but some of you might be intimidated by it. But really, just listen to the theory of what's going on here. So whenever you have a launch angle, something launching at an angle, you have a vector, and so it's launching at 10 meters per second, and it's going at some angle. Okay, alpha is the angle. What you can do in engineering is to find out what's the optimum angle is the idea here for these next few pages. What you can do is you can when you have a vector, you can always you think of that vector as this is a vector in a certain direction. This is the y component of that vector, and this is the x component of that vector. And just simple trigonometry will tell you the values of those things. This is a triangle, and you can figure out, if you know alpha, you can figure out and v, you can figure out what v in the y direction and v in the x direction is. Okay, and those are pretty simple equations, but you got to know a little bit of trigonometry. Okay, so the horizontal displacement, now t is the time of flight. Okay, it's going to launch and it's going to go flying over, and 1 or 2 seconds later it's going to land. Okay, so if we need to determine what t is. T, the velocity in the x direction, assuming we don't have any aerodynamic drag or very little aerodynamic drag, that's just going to be the initial velocity in the x direction times the time of flight. And the vertical displacement, you can think of this as the canister being launched sideways and without much friction, and how far it would go. and it would still be going the same velocity when you were done there if you didn't have any friction. But it's going to stop because time's going to run out. And the velocity in the motion in the y direction is going to tell you how long it goes. So you can think of this as a canister launched straight up and straight down just along this velocity. And Vy is a smaller velocity than this velocity that's launched at. But you can see how much time it is. If you did just throw up in the air and throw it down, you can find out how much time it took to do that by this equation. Y equals the initial velocity in the y direction times the time minus 1/2 times the gravitational constant times time squared. And that's a law of motion, um, an equation for getting that. But you can see if I know so here's what we do. The horizontal component of this launch vector is VO cosine theta. And you know that because it's adjacent over hypotenuse. And the velocity in the y direction is this initial velocity times the sine of theta. Okay. And then you calculate the time of flight in the second equation, the up and down equation. You say the height, y is 0, which is equal to the initial velocity times time times 1/2 times in other words, gravity is working downward on this. And so it has an initial velocity, it goes up and it stops, then it comes down. So what is the time it takes to go up and come down? And we solve for time. We get this, so now we know what the time is in terms of initial velocity and the angle theta. And that's g is always 9.81 meters per second squared. So now I know what time I substitute time t into the other equation, the x-axis equation, which was the range r is initial velocity times time. Now I substitute the time term I got here, I substitute here. And I'm saying it goes up and comes down, and that amount of time can tell me how far it went. Okay, I separate the y velocity, what's happening in the y direction is separated from what's happening in the x direction. So now I've solved for t, which is the common thing between them. They take the same time, and I substitute in there, reduce some things, and I come out with this equation. The initial velocity squared times the sine of 2 theta. I guess they've got, and divided by g, the constant. And if you look at this equation, you know something about trigonometry, you know that this will reach its maximum. In other words, this will be the biggest it can ever be when the angle is 2 theta. Okay. And so you say 2 theta equals 90 degrees, and the perfect angle to launch at is 45 degrees. So and we can verify that by launching at different angles. This is my variable angle launch pad. And then the last thing I'll cover is all these variables you're thinking about, whether it's the weight of the water, how much water is in it, is the water cold or hot, is the tape on or not on, is there fins, is there a nose cone, is there nose weight, and what's the launch angle. So there's a whole bunch of variables there, and you really only want to change one thing at a time. So you do your first test with one set of variables, and you write down how much it's flown. Then the next time, maybe I put more water in, and I keep everything else the same, whatever it is. Maybe I don't have tape on it. I don't have fins on it. I use cold water. No nose weight. So I start out with none of these on here, and then I do 4 or 5 of these. And if the cap release is consistent, then I say, hey, more water or less water resulted in this, and I can draw a conclusion from those number of tests. And the reason I make this matrix is this gives you a number. So ASR 001, 30, CNNN, and 60. That tells me exactly what that rocket is and what the independent variables were. Then I go down here and I say, okay, now I keep the water weight the same and I do hot and cold. And I do five each of those. And then I say, hey, they either went further or didn't go further. They launched quicker or not quicker. But what I really want is how far they went. And then I know that whether I want to use hot or cold water. And then I can say, put the tape on there. Did that increase the launch pressure? Did it hold the cap on a little more? Try it with it, keeping everything else the same. Try it with and without the tape, and then decide if that's worth doing. And then and then start over. Do I want fins on it or not? Did it fly straighter? Did it go further? Nose weight or not? A nose cone or not? Did it fly straighter? Do five with and without. Nose cone weight or not? Five with or without. And then finally, or you can do this first with everything exactly the same. I launch it five at 60 degrees, five at 30 degrees, and five at 45 degrees, and generally and see which ones. Now, if the cap is leaking and some of them don't launch, I would just not count that as a test at all. You don't say, well, this one flew zero, because that's just going to screw up your whole. So they have to launch. Now there is an occasion where some of them just launched a little bit and went 5 feet or something like that, and I would say, well, that thing leaked, and we're going to discount that test because um, if you put that into an average of 5 flights, you're going to get the wrong answer probably. So first order of business is to get a more consistent cap seal. And I'm sorry, this is not a conclusive effort here. That basically I'm saying until you get a consistent cap that always releases at the same pressure, um, it's going to be difficult to sort out all the other variables because you don't know which is making it better. Okay. So if you do this, keep that in mind and uh, and always draw the right conclusion from what your data says. Okay. Think I'm done. Thanks.